Welcome to MathInvent. In this video, I will discuss some questions from CSIR NET 2020 session. These questions are from the chapters Sequence and Series on Real Numbers. So let's get started. The first question here is asking about limit of this sequence. Either it is equal to e by 4, 4 by e, or it doesn't exist. So let xn be this series, xn be this sequence. So n plus n power 1 by n divided by n. First we need to manipulate this term a little. So if we take n common out from each of these terms, we will have, there are n terms, so there will be n power n, then we will have 1 plus 1 by n, 1 plus 2 by n, up to 1 plus n by n, and this is whole power 1 by n divided by n. So if we take this power and this 1 by n, it will get cancelled out. So we will have n into 1 plus 1 by n, 1 plus 2 by n, up to 1 plus n by n. This whole power 1 by n and n. So here n and this n will get cancelled out. So we have xn equals to this series. Now take a look at this sequence. We have these terms multiplied and this is on the power. So if we take log here, we will have log xn equals to 1 by n into log of 1 plus 1 by n plus log of 1 plus 2 by n up to log of 1 plus n by n. Okay, so this can be written as, if we write this in the summation form, we will have 1 by n, r is running from 1 to n, log of 1 plus r by n. So log xn equals to this. We are trying to find here what is limit n tends to infinity log xn. So from the 12th standard we know a result. It is the standard result for definite integral, integration 0 to 1 fx dx. This is equals to limit n tends to infinity 1 by n summation r runs from 1 to n f of r by n. So here we have f of r by n. So here the function fx is log of 1 plus x. So this log of xn, so log of xn will be equals to integration 0 to 1 log of 1 plus x dx. So we need to find this integration. So let us find this integration first. Integration log of 1 plus x dx. So we will have to use the integration by parts. So here we will have x, we are taking log of 1 plus x as the first function and dx as the second function. So x log 1 plus x minus integration, derivative of log of 1 plus x is 1 by 1 plus x and integration of dx is x dx. So this x can be written as 1 plus x minus 1 dx. So x log 1 plus x minus, if we separate this term from here, we will have 1 plus x divided by 1 plus x. So it will get cancelled out and we will have 1. So integration dx. So minus x minus, and this minus will become plus. Then we will have integration dx by 1 plus x. So this is log of 1 plus x. So here we will have x plus 1 log of 1 plus x minus x, 1 0. So if we put the upper limit first, we will have 2 log 2 minus 1, and if we put 0 here we will have log 1. The value of log 1 is 0 and here we will get 0. So 2 log 2 minus 1, this can be written as log 4 minus log e. So this can be written as log of 4 by e. Okay. So here this term should be equal to, let us take limit here, limit n tends to infinity. So if limit n tends to infinity, log of xn equals to log of 4 by e, then we can write limit n tends to infinity, e power log of xn equals to e power log of 4 by e. So from here we will have limit n tends to infinity, xn equals to 4 by e. So this limit will exist and this limit will be equal to 4 by e. So here the correct option is option B. Okay. So we have done the first question. Now let us take a look at the second question. So we have the next question here. We need to find the sum of this series, this infinite series. So here we are given s equals to half minus 1 by 3 into 1 factorial plus 1 by 4 into 2 factorial and so on. Let us observe one thing. In each of these terms, here we have 1 factorial into 3. Here we have 2 factorial into 4. So here is a 2 missing. If we multiply by a 2, then we will get 3 factorial. Here is a 3 missing. So if we multiply by 3, we will get 4 factorial. Here if we multiply by 4, then we will get 5 factorial. So let's do that. So half minus, we are multiplying by 2 in the numerator and denominator. So we will have 2 by 3 into 2 into 1. So this is 3 factorial plus, here we are multiplying by 3 and 3. So here it will be 3 and here it is 2 factorial into 3 into 4. So it is 4 factorial minus here 4 and 3 factorial into 4 into 5. So 5 factorial, so on. Now we can make this 2 as 3 minus 1. We can make this 3 as 4 minus 1. 4 as 5 minus 1. So let's do that. So we are writing 1 as 2 minus 1 divided by 2 factorial minus 3 minus 1 by 3 factorial plus 4 minus 1 by 4 factorial minus 5 minus 1 by 5 factorial, so on. If we separate these terms, we will have 2 by 2 factorial, it will be 1 minus 1 by 2 factorial here we have minus 3 by 3 factorial. So 3 and 3 will get cancelled out. We will have 1 by 2 factorial. Minus minus plus 1 by 3 factorial plus 4 by 4 factorial. So it will be 1 by 3 factorial minus 1 by 4 factorial. Here minus 5 by 5 factorial. So it is 1 by 4 factorial plus 1 by 5 factorial and so on. Now here we are getting 2 by minus 2 by 2 factorial plus 2 by 3 factorial minus 2 by 4 factorial. So let us take a look at a series e power minus x. What is it? It is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial plus x power 4 by 4 factorial and so on. So if we write e power minus 1, so we will have 1 minus 1 plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial, so on. So here if we take a minus 2 common out, here we have 2 by 2 factorial plus 2 by 3 factorial minus 2 by 4 factorial plus 2 by 5 factorial, so on. There before 1 by 2 factorial we have plus, here we have minus, so we are taking minus 2 common out. So we will have 1 by 2 factorial plus minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial, so on. So 1 minus 2 into, what do we need more? 1 minus 1. So 1 minus 1 we can take that as it will be 0 plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. So it is E inverse. So we have 1 minus 2 E inverse, that is 1 minus 2 by E. So here the answer will be 1 minus 2 by E. So let us see the next question. This question is from part C. So it can have multiple correct options. The last two questions were from part B. So let us see the first option. If two subsequences x2n, okay, the sequence here, it should be like this. The sequence here is a sequence of positive real numbers. If two subsequences x2n and x2n plus 1 converges, then xn converges. So these two sequences are complementary subsequences in xn. Complementary subsequence. What do we mean by complementary subsequence? Complementary subsequences are like this. Suppose we have a sequence xn. If it has two subsequences xnk1 and xnk2 such that condition 1, nk1 union nk2 will give the whole natural number, and 2, nk1 intersection nk2 equals to 5. So here we have the same condition. Here 2n and 2n plus 1 will give the whole natural number, and intersection 2n intersection 2n plus 1 will be 5, since these are the even numbers and these are the odd numbers. So these two converges implies every complementary subsequence converges, so xn will converge. Xn converge. Let us check the next option. So option 2. We are given if minus 1 power n xn converges, then sequence xn converges. Suppose let us take this as yn equals to minus 1 power n xn. So if yn converges, then we have to show that if it is true, if yn converges, then xn will also converge. Okay. Let us take a look at y2n and y2n minus 1. Okay. So y2n will be minus 1 power 2n x2n. So minus 1 power 2n will be plus 1. Here it will be x2n. And y2n minus 1 will be minus 1 power 2n minus 1, minus 1 power some odd number. So it will be minus x2n minus 1. Now what is given here? This xn is a sequence of positive real numbers. So this is a positive term. This is greater than 0. x2n minus 1 positive term and there is a minus before it. So it is a negative term. So y2n is positive and y2n minus 1 negative. Now it is given that yn is convergent. So yn convergent, this implies limit yn exists. So we know that yn converges. This implies limit yn equals to limit y2n. Suppose limit yn be y, limit yn equals to limit y2n, limit y2n minus 1. Since if a sequence is convergent, then every subsequence of it will also converge and it will converge to the same limit. So we have limit yn, since y2n is greater than 0, so limit y2n should be greater or equals to 0. And since y2n minus 1 is less than 0, so limit y2n minus 1 should be lesser or equals to 0. So from these two we have y greater or equals to 0, y lesser or equals to 0. This implies y should be equals to 0. So what we have proved here is that this sequence here is convergent and this converges to the limit 0. So now we need to prove that xn is also convergent. Okay. So yn is convergent. Let epsilon greater than 0. Since yn is convergent, there exists by definition of convergent sequences, there exists a k belongs to n such that mod of minus 1 power n xn minus 0 less than epsilon for all n greater than k. So minus 0, so here we have mod of minus 1 power n xn less than epsilon. So this implies mod xn less than epsilon for all n greater than k. So xn is convergent and limit xn is also equals to 0. So here we have proved that xn is convergent and we have also find its limit, that is 0. Okay. So option 1 is correct, option 2 is correct. Let us check the rest two options. Okay. So first let us check the option 3. Limit n tends to infinity, xn plus 1 by n exists, then xn power 1 by n will be bounded. Okay. Let L equals to limit n tends to infinity xn plus 1 divided by xn. Fix epsilon greater than 0. This is fixed. Then there exists a k belongs to natural number such that xn plus 1 divided by xn minus L less than epsilon naught. So we have here xn plus 1 by xn less than L plus epsilon. This implies xn plus 1 less than L plus epsilon into xn. So this holds when n greater or equals to k. So if we use this result, what we have here, xn plus 1 is less than L plus epsilon xn. If we use the same result for xn, we will have L plus epsilon square xn minus 1 okay. So continuing in this way, we will have this holds when n is greater or equals to k. So we can go till k, xk. So L plus epsilon power, here we have k. So if we put here n minus k, here will be n minus k plus 1. So n minus k plus 1. Okay. So from here we have xn plus 1 less than L plus epsilon power n plus 1 xk by L plus epsilon power k. Let A equals to xk L plus epsilon power k. This is a positive real number. So we have xn plus 1 less than L plus epsilon n plus 1 into A. So this implies xn plus 1 power n plus 1 less than L plus epsilon into A power 1 by n. Okay. So we are given here xn power 1 by n. This is same as xn plus 1 power 1 by n plus 1. This is less than L plus epsilon A power 1 by n. We know that as n tends to infinity, if A is any positive real number, this implies limit A power 1 by n will tend to 1. Means A power 1 by n is a convergent sequence. So L plus epsilon into A power 1 by n, this term converges, implies bounded. So this term is convergent, implies this is bounded. If it is bounded, this term here is less than this term. So if it is bounded, it should also be bounded. So what we have proved here, this implies xn power 1 by n is bounded. Okay. Actually, there is a standard result if limit n tends to infinity, xn plus 1 divided by xn equals to L. L can be 0, L can be non-zero real number, or L can be any infinite number. Then this series here, this sequence here, xn power 1 by n, this will converge to the same limit L, provided these sequences should be sequences of positive real numbers. Okay, so option 3 is also correct. Let us see the option 4. If the sequence xn is unbounded, then every subsequence is unbounded. So let us construct an example. Take xn equals to 1 n when n is odd, when n is even. Okay, so n natural number is unbounded, so this sequence xn should be unbounded. So xn unbounded, but if we take x 2n minus 1, this is 1. Every term of this sequence x 2n minus 1 is 1. So x 2n minus 1 is bounded. So this is a false statement in general. So this statement is false. So here the correct options are 1, 2 and 3. Okay. So we have done every questions which were asked in the CSIR NET 2020 exam from this chapter, series sequence on real numbers. Thanks for watching this video and subscribe to the YouTube channel MathInvent. Thank you.